Hello everyone and welcome to this session on inferences from two samples. My name is Vamsidhar. In our earlier chapters, we had a look at some level of inferential statistics where we did hypothesis testing relating to the claim of proportions. Then we also did claim relating to the mean of a sample, mean of a population from one single sample. Again, when the population standard deviation is known versus standard deviation is not known. And along with that, we also tested on the standard deviation or the variance of the population. So, primarily, these were all, if we see, these were the hypothesis tests when I have compared or when I have tested the values against a hypothesized value in an absolute sense, proportion greater than 40%, or probably mean height 170 centimeters. So what we have observed in these kind of claims was the comparison or the hypothesization or the claim is always against a fixed value. Variance is equal to 15%. So it was against a constant value. So whenever the claim was against a constant value, we can use that one sample test either for proportion, mean or variance. And what we have observed is in case of proportions, we use a Z statistic for mean. In case I know the population variance, I use a Z statistic, otherwise I use a T statistic. And in case of variance, we use a chi-square statistic. But not all the times our claims or comparisons will be with a constant value. Sometimes the comparisons will be with another population parameter. So it would be between, I have to take two different samples, and based on the two different samples, I may have to give the conclusion regarding a population. So wherever we are making a conclusion not against a fixed value but in comparison with another population, one population's parameter in comparison with another population's parameter, that is where we use the concepts that we are going to discuss in this particular session. And again, it could be with the proportion, but here the test which we would be looking at is not comparing the proportion with 40%. Probably comparing the proportion of votes of party 1 with respect to party 2. So party 1 data I have to take one sample, party 2 voters I may have to take some other sample, and based on that I will have to do the claim, accept or reject. But at the end, the fundamentals of hypothesis testing are going to be retained. So as a part of this session, our focus is on how do I evaluate a claim with respect to two proportions? Is proportion 1 greater than proportion 2 or vice versa? Can I say that this particular party will definitely get more seats or more votes compared to the next political party? Right? If I have to make such kind of conclusions, I'll use the inference about two proportions. If I have to talk about the inference about the two means, for example, the mean height of an Indian is less than the mean height of an American. So this is a claim that has been made. Mean height of an Indian is less than the mean height of an American. So here I am not having a fixed constant value. The hypothesizing is across two different populations. And again, this kind of claims, if I have to test out, or sometimes I can have the two different samples. Here we are talking of independent samples. Indians is a set of sample, Americans is a set of sample, and probably there is no dependency or overlap between the two samples. So if I have to do some kind of hypothesis testing or claim testing across two different independent samples of data, what is the kind of statistic we use, and based on that, how do we evaluate our claim statement, is what is covered here. In case the samples are dependent, generally applied for before and after scenario, or probably for the two variables that are highly related, probably height and weight. For the same person, I would be taking the height and the weight and then seeing is there any difference between the heights and the weight, or mean height of a male is greater than his spouse. Mean weight of a male person is always greater than the mean height of his spouse, which means there is a dependency. Like they cannot be independent data altogether. So I can very well look at a person and his spouse, and say such kind of samples as dependent samples. So if I want to find out any kind of inferences about the mean difference between a male and his spouse in terms of height or weight, is there any significant difference from that standpoint, we can look at the inferences from dependent samples. This is one more thing that we can look at. And finally, if I want to look at the comparing the variances in the two samples, even that can be looked at. So let's say the standard deviation of Infosys returns is greater than the standard deviation of the Wipro return, or the standard deviation of the heights of Indians is greater than the standard deviation of the heights of the Americans. So when I am not comparing the means, but I am comparing the standard deviations, I can use the other test. But in all these cases, remember the simple fundamental for you to understand is, first create null hypothesis. In all the null hypothesis, if I am talking about the proportions, my null hypothesis always is the proportions are equal, because null hypothesis should contain equality, or greater than or equal, or less than or equal. Then similarly, when I am talking about the means, I will say the population mean 1 is equal to population mean 2, or greater than or equal to, or less than or equal to. Equal to should definitely be there as a part of the null hypothesis, and alternate is the opposite to that. Same thing with the variation or variances or standard deviation. The standard deviation of the population 1 is equal to the standard deviation of the population 2. So you know the null hypothesis in each of the cases. Then we are looking at the alternate hypothesis, which is not the null hypothesis case, or which is the opposite to that of the null hypothesis case. Right, so we'll look at the proportions. Now here we should talk about two proportions, P1 and P2. So I am going with the null hypothesis that P1 equal to P2. If that is the case, then my alternate hypothesis will become P1 not equal to P2. Then P1 is nothing but the out of a sample. Now if I go with the samples, I will take two different samples, one from a population 1 and the other one from a population 2. So I may take the same sample size for both, or I am taking two different sample sizes. So let's assume I am taking two different sample sizes, N1 in the first case and N2 in the first case. And out of this N1 which I have looked at, let's say X1 are constituting that proportion, and in the second case, let's say x2 are constituting the proportion. So P1 will come out P1 cap, which is from our sample, because from sample I have to compute P1 and P2. So here I am taking a samples maybe of the same size, or sometimes I may not have the data of the same size. So I am resorting to two different samples of two different sizes, N1 and N2 respectively. And out of that, whatever the number of, let's say here we are talking about the proportion of votes. Let me create an example that makes it easier for you. So here I would like to test the scenario that the proportion of the votes for a particular political party A in state 1 is same as the proportion of votes which they get in state 2. That is what is the thing which I am looking. This is my null hypothesis. So proportion in state 1 is same as proportion in state 2. That is what is the null hypothesis. If I say the not equal to relationship, then it goes as alternate hypothesis. Right? Now I have to take the samples. Because there are two different populations, I have to take two different samples. So there is a possibility that I may take the same sample size, or depending on the size of the state, I may go with different sample sizes. So N1 from the first sample and N2 from the second population. So out of that, let's say some X1 people have voted for this political party A, whereas in state 2 some X2 of them out of the sample which we have selected, they have voted for the political party A, which means our proportion in this case is equal to x1 by n1, which is obtained from our sample. Similarly, the second proportion obtained from a second sample is x2 by n2. Whereas our null hypothesis is P1 equal to P2, whatever is the population proportions of both of them. So alternate will become P1 not equal to P2. Now, from that case, I also come up with what is called as a pooled proportion. In this example, we compute one more, before we compute the test statistic, we compute what is called as a pooled proportion, which says, now that you have taken a sample of N1 and N2, overall, you have taken N1 plus N2 people, and out of this N1 plus N2 people, X1 plus X2 have voted for political party A. So this particular proportion, whatever it is what we call as the pooled proportion. So P bar, which is what is called as a pooled proportion, and the corresponding Q bar, who have the proportion of the people who have not voted for the political party, is going to be 1 minus P bar. So that's one more calculation called as the pooled proportions that we do in this case. And then, as simple as it, now the difference in our sample proportions, which is P1 cap minus P2 cap, whatever is the difference in our sample proportions, minus the difference in the population proportions. Because we have made a hypothesis that both of them are equal. If that's the case, P1 and minus P2 will always be 0. But in some cases, what we will also make is P1 equal to P2 plus 2, which means this particular party in state A will get 2% of the votes more than state B. If that is the kind of hypothesis I may have to look at, then my equation will become P1 equal to P2 plus 2. Then P1 minus P2 will become 2. So depending on the kind of claim which I am making, because this is also an equal to relationship, depending on the claim which I am making, I will frame my null hypothesis accordingly. Whereas the test statistic here is very simple. The difference between your sample proportion, both the sample proportions, minus the hypothesized difference between the population proportions. When you hypothesize that both the populations are equal, then the difference between the population proportions is 0. If you hypothesize there will be a difference of 2%, then the difference between the two population proportions is 2%. So depending on what you have hypothesized, you will take P1 minus P2, and in the denominator you are taking the standard error, because there are two different populations. Our standard error is square root of p bar q bar by n1 plus p bar q bar by n2, because we have taken two different samples of two different sizes, but in both the cases we have taken p bar, which is the pooled variance, and using that pooled variance we have arrived at the standard deviation or the standard error of the entire two sets of samples. So the standard error is going to be this much. So based on that you are computing the test statistic. So for a proportion, even for one single proportion it was following a Z statistic. Even in case of two different populations, when it is about testing a proportion, it will be following your Z statistic itself. The sample proportions minus population proportions, the anticipated population proportion difference, divided by the standard error, which in this case will come out as root p bar q bar by n1 plus root p bar q bar by n2. So this is your test statistic. The moment you have your test statistic, we know that it is a Z test. So based on this, I can find out the critical values. If I am talking about 95% confidence interval, right? Because our null hypothesis is equal to, alternate is not equal to, which means the rejection zone will be on both the sides. It's a two-tailed test. If the rejection zone is on both the sides, then my critical values for a 95% confidence interval are minus 1.96 and plus 1.96. Then I will see whether my test statistic is within this minus 1.96 to plus 1.96, or it is in the critical region, which is outside these limits. If it is outside these limits, I'll reject the null hypothesis and say there is a difference between the proportions of these two populations statistically. Otherwise, I cannot reject the null hypothesis and say there is not much of a difference between the proportions of these two statistics. That's a straightforward way. And if I am using p-values, as I said in the earlier chapter also, the statistical tools like Excel and SPSS are very comfortable in terms of giving your p-values. When you are using the p-values, all you may have to do is compare your p-value with the level of significance. If the p-value is less than the level of significance, then you reject the null hypothesis and go with the alternate hypothesis, saying there is no equality, or there is a definite difference between the proportions of two populations. Otherwise, you cannot reject the null hypothesis and you may have to go with the statement there is no difference between the proportions of the two populations. But to execute this, a few things we have to be keeping in mind. There are a few requirements for making the claim before we actually get into the calculation of the test statistic and the critical values, and then either rejecting the null hypothesis or failing to reject the null hypothesis. I have to make sure that the two populations which I am taking, the two proportions which I am collecting for two different samples, they are independent samples and they are collected on a simple random basis itself. They cannot be dependent samples. The values are purely independent. That's one of the things. And both of them, because we are approximating a binomial distribution. Why do we say binomial distribution? Here there are only two possibilities. Either they have voted for party or not voted for party. So only two possible outcomes, success and a failure. So because we are talking from that dimension of success and failure, actually it has to be a binomial distribution. But we are using the Z test, which means we are approximating a binomial distribution to a normal distribution. And as we have discussed in our earlier chapters, whenever I want to approximate a binomial distribution to a normal distribution, this particular condition should be definitely satisfied. Your NP should be greater than or equal to 5. and NQ should be greater than or equal to 5 for each of the two samples. If that is not the case, then obviously I cannot use this entire hypothesis testing procedure. So remember, assuming all the requirements are met, you can test the claim about the two population proportions using this z-test. All you require is first establish your null hypothesis, collect the sample data of two different populations. From that, find out what is the sample proportion 1 versus sample proportion 2. Find out the differences between the two sample proportions and what is the hypothesized difference between the two proportions. And the way you find out the standard error is you first pool the proportions by taking the total population, total sample which you have taken, and the total number of people who have voted for that party. So based on that, you compute the pooled proportion and take the Q, which is 1 minus the pooled proportion, and use it for computing your Z statistic, compare with the critical value, and make your decision. Sometimes I may be more interested in finding out the confidence interval also of the differences. What is the range of these differences? The difference between P1 minus P2, what could be the minimum value, or what are the ranges? P1 minus P2 minus some margin of error plus some margin of error. So what is the range in which the difference is going to lie with a 95% level of confidence? So we have been talking about the margin of error as a calculation which is a multiplication of critical value multiplied by standard error. Standard error we have calculated in the earlier, we have used in the earlier case the P bar Q bar by N1 plus P bar Q bar by N2. That is your standard error in case of two proportions. You multiply it with the critical value. If I want 5% level of significance, you multiply it with 1.96. So this will be my margin of error, and this particular margin of error you subtract it from P1 minus P2, you add it to P1 minus P2. That will give you the confidence interval, 95% confidence interval of P1 minus P2. And how do you say that, how do you go to test the equality of the two proportions? If the value 0, if the value 0 lies in between this range, P1 minus P2 minus the margin of error and P1 minus P2 plus the margin of error, within this range, if 0 is present, or if our hypothesized value, whatever is that, if the hypothesized difference between the two proportions, right? If I am hypothesizing as both the proportions are equal, then 0 is the hypothesized difference. If that hypothesized difference lies within this range, then I cannot reject the null hypothesis. If the hypothesized difference does not lie within this range, then I can reject the null hypothesis and I'll go with the alternate hypothesis. So either for making a conclusion based on the confidence interval, or to understand what could be the clear cut difference in the proportions of both the datas, I can very well use this finding out of the confidence interval and attaching the margin of error, which is calculated based on the critical value and the standard error value. So if the confidence interval limits contain 0, then I cannot reject the null hypothesis. If it does not contain the 0, then I can very well reject the null hypothesis and say that both the proportions are really different. Now, moving on to our next test. Inference about the two means. So again, a simple null hypothesis is mu1 equal to mu2. Or sometimes if people say, yeah, we are talking about the average height of Australians is 5 centimeters more than the average height of the Indian. We are not talking about equality relationship. When I try to establish in a mathematical form, the average height or the mean height of an American is equal to mean height of an Indian plus 5. I want to test not the direct equality, but I want to test the equality where Indian plus 5 is taken, which means the difference between the means is going to be 5 centimeters. Again, the same logic. Take the samples of Indians, take the sample of Americans, right, and find out the mean of the Indian, mean height of the Indians, x1 bar, mean height of the Americans, x2 bar, and the standard deviations of the heights of the Indians, s1, and the standard deviations of the heights of the Americans, s2. So again, in case we don't know the population variance, just equate it to your individual one single sample t-test itself. In case we don't know anything about the variance of the population, we are trying to find out the variance from the sample itself. Then we are going to use the t-test, not the z-test, which we have seen earlier also. So the t-test is going to be the difference between the two sample means, x1 bar and x2 bar, minus the difference between two hypothesized population means, which is mu a minus mu I, probably 5 centimeters in this example. But if I talk about the equality between the two samples, then the difference is always equal to 0. So, but the mechanism is the sample difference, sample mean difference, minus hypothesized population mean difference divided by the standard error. And in the standard error case, for case of only one sample, we had taken as s by root n, whereas when it comes to two different samples, we'll take it as s1 squared by square root of s1 squared by n1 plus s2 squared by n2, which is nothing but if s2 was not been there, it would have boiled down to s1 by root n itself. So when I am taking two samples from two different datas, it works out to be square root of s1 squared by n1 plus s2 squared by n2. So this is what is a t statistic. And so for this t statistic, I also need to know the degrees of freedom, because if I have to find out the critical value for t, if I want to find out the critical value for z, all I need is the level of significance only, alpha. Whereas if I want to find out the critical value of t, I need two things. I need the level of significance and also the degrees of freedom, because the t value differs for different sample sizes. So I need the degrees of freedom. In one single sample case, the degrees of freedom was straightforward. Number of samples minus 1. Whereas if I am talking of two different samples like this, there are two schools of thought. One of them says you take the minimum of n1 minus 1 and n2 minus 1, whatever is the smallest of these two, you take it as the degrees of freedom, and based on that, for a particular level of significance or 95% level of confidence, you try to find out your t statistic. But there is one more derivation that have been done by the people, where they have come up with a slightly complex calculation of the degrees of freedom, where it is being said, again different tools, they use it in different way, or if you are using Excel, you can directly plug in this formula and try to compute the degrees of freedom. So there is no point in memorizing all these things, but a simpler way of getting into the degrees of freedom for this kind of an approach is you can take the minimum of n1 minus 1 and n2 minus 1. Otherwise, you find out s1 squared by n1 separately, s2 squared by n2 separately, and name them as a and b, make it as a plus b whole squared divided by a squared by n minus 1 plus b squared by n2 minus 1. That would typically work out to be your degrees of freedom. But that degrees of freedom will help you in computing your critical value. Again, you are seeing based on the critical value, you can identify the critical region and then you will see whether your computed t statistic is lying in the critical region or not lying in the critical region, and based on that either you are rejecting the null hypothesis or failing to reject the null hypothesis. The concept is still the same, but in this case a few things that need to be met. The sample should be completely independent, right? There should not be scenarios like before and after. Here Americans, Indians, two different populations altogether, so the samples are completely independent. And few more things I have to make sure is I should not know the variances of the populations, right? No idea about the population variances or standard deviations, so that's where we are using S. We are computing it from our sample, and at the same time we are using the t distribution, because we cannot use the z distribution if the population variance is not known. So one mandatory requirement is population variance should not be known, and I should definitely assume that they are not equal. If they are equal, if they are assumed to be equal, we have another mechanism. We'll also talk about it in the next couple of slides. We bring in a concept of pooled variance. Just like the way we have brought in pooled proportion, we bring in a concept of pooled variance in case we come to know that the variances, though they are unknown, but I am assuming them to be equal. If they are assumed not to be equal, then I have to go with then only I can use this particular t-test. And yeah, either because we are talking about a t distribution, this will work. This t distribution will work only if I'm assuming that the data, that both the populations are coming either from a normal distribution, or at least the sample size is greater than 30. At least one of these two conditions need to be satisfied if this particular test needs to be applied. So there is one part which is the calculation part, and comparison with the critical values, and making making a claim about the hypothesis, making a conclusion based on the hypothesis. Two, understanding the basic requirements to implement this particular test, because only in some particular cases any test can be implemented, and there are some limitations about the implementation of a test in some cases. So even the requirements aspect of it need to be understood in great level of detail. All right. Now sometimes I would be interested, just like in our earlier proportions case, I would be interested in finding out the confidence intervals also for the difference. The confidence interval of the differences, very clear. Find out the sample difference. Find out the sample, whatever is the difference between the two samples. Then you subtract the margin of error from it. You add the margin of error to it. Margin of error again is the critical value. In this case, because we are using the t distribution, I'll use the critical value corresponding to the t. And at the same time, because the standard error, we have already found it in our previous case, root of s1 squared by n1 plus s2 squared by n2. Based on that, I will get my margin of error, subtract that margin of error from the difference, and add that margin of error to the difference. So this gives me the confidence interval. And whatever is the hypothesized value, let's say my hypothesized value is 0, hypothesized difference between the two means is 0, then 0 should be present in this confidence interval. If 0 is not present in this confidence interval, then I will reject the null hypothesis and say that the means of these two populations are different. If 0 is present within this confidence interval, then I don't have any evidence to say that there is a difference between the means of these two data. So I may have to go with there is no difference between the two sets of data itself. So about the means, if the samples are completely independent, I can use this mechanism of testing. Two different populations which are completely independent. When I say independent, like India and America, it should not be man and his spouse. Then they are called dependent samples. The weight of the person before and the weight of the same person after a treatment. These are all dependent samples. But when I am saying independent, no relationship. an Indian data which is a completely separate data from an American's data. A male data which will be completely different from a female data. But when I say male and his spouse, there is a dependency. But when I say male and female population, they are completely independent. Right? Now, in case the population variances are known, then all the difference is I have to replace S1 with sigma 1, S2 with sigma 2, and the t test will become a z test. Nothing much. So the critical values also will come from the z table or the normal distribution table instead of the t table. Right? Everything else remains the same. In case the means are, in case the standard deviations of both the populations are known. If they are not known, I have to compute them from the sample, and because I am computing them from the sample, I have to use a t distribution with that much of degrees of freedom. Whereas if they are known, if the population variances are known, I don't need to go for a t test, I am going for a z test, and when I am going for a z test, I don't need degrees of freedom, because the critical value for a z test comes directly only from the level of significance only. Then the third scenario is when the population variances. So there are three scenarios regarding the testing of the means of the independent samples itself. In the independent samples, one kind of scenario is variances known. Then I am going for a z test. Variances not known and not equal. Assume not equal, which means the earlier scenario where we have talked about the standard error as root of s1 squared by n1 plus s2 squared by n2, and that t test which was t statistic which was talking about x1 bar minus x2 bar minus of mu1 minus mu2 by square root of s1 squared by n1 plus s2 squared by n2, and overall resulting in a degrees of freedom of that very large formula. But if I am saying variances are not known, but I am assuming them to be equal, then this is the kind of scenario which we are going to generate. So the test statistic here is a straightforward one. S1 x1 bar minus x2 bar, mu1 minus mu2, numerator is not going to be different, but the standard error is assumed to be different. Earlier we had a standard error of square root of s1 squared by n1 plus s2 squared by n2. Now if I am assuming the population variance to be the same, generally what has come out is a concept of pooled variance has come out. The pooled variance is coming out like this: n1 weighted average, n1 minus 1 into s1 squared plus n2 minus 1 into s2 squared. Look at it, this looks like a weighted average, right? n1 minus 1 into s1 squared plus n2 minus 1 into s2 squared divided by n1 minus 1 plus n2 minus 1. This is like a weighted average variance is what is taken as a pooled variance, sp squared, and your standard and your variance will simply come out as sp squared by n1 plus sp squared by n2. This is one small difference that you are having. In case the population variance, though it is not known, but if you are assuming that it is going to be the same, you will use this mechanism. So your t statistic is computed through this, and the t statistic is compared with the t distribution, the critical values based on the level of significance and degrees of freedom, which is n1 plus n2 minus 1, and based on that you are trying to go with either rejecting the null hypothesis and going with the alternate, or failing to reject the null hypothesis and go with the null hypothesis itself. So here all you have to know is, yes, I am trying to find the means. I am trying to make the comparison between the means of two populations. But all I need to know is for this population, is the variance first of all known. If the variance is not known, if am I assuming that both of them could be equal, or am I assuming they are not going to be equal? In this kind of three different scenarios, I'll go for three different kinds of tests. Whatever is the test statistic that is coming out, based on that I should be able to identify my critical value, and based on the identification of the critical value, I need to look at whether the decision needs to be rejected, whether my null hypothesis need to be rejected, or it has to be failed to be rejected and going to be accepted itself. Similarly, if I want to go for a confidence interval estimate, also the same thing. Take the sample, whatever is the difference between the means of two samples, subtract the margin of error, add the margin of error. And what is the margin of error? It is the critical value which is obtained from the t statistic multiplied by the standard error. In this case, our standard error is square root of sp squared by n1 plus sp squared by n2, and sp squared comes out as the weighted average variance of the two individual sample variances. So using that information, I can make a conclusion about the claim whether the two means are equal or different for two different independent samples, depending on whether the variances are known or not known, or even if they are not known, are they assumed to be equal or not equal. These are the three different types of tests for comparing your population means of two different populations, right? So the third kind of scenario which we are going to look at here is from dependent samples. We are not talking of independent. Typically before and after kind of examples, right? I would like to find out, is there any big difference of the medicine? Let's say a doctor is prescribing a particular drug to a large number of patients. He is making a claim that my medicine will reduce your weight by 10 pounds. So I have to really collect the data if I want to find out whether the medicine is really effective or not, or whether it can really reduce the weight by 10 pounds or not. I have to collect the sample weights before the treatment started, and for the same person I have to collect it after the treatment has ended. So there is a lot of dependency between the samples. Similarly, if I want to find out what is the is there any specific age differences between a man and his spouse? If that's the kind of statement I may have to look at, then there is a dependency in the sample. I cannot take a man and some other women data, because here we are talking about the age of the man as well as his spouse. So once I select one value independently, the other is dependent on the original value itself. So it goes as a pair rather than independent. So they are called as paired sample data also. In that case, it's always about the differences between the two dependent samples, which means before and after, or a person and his spouse. So in that, is there any kind of a differences? So the differences are not at the mean level, but at every individual sample level, what is the mean difference? That kind of test is what is applied for dependent samples. And in this case, the test that is applied is, so we are saying the hypothesizing that there is no difference, which means before and after the weights are going to be the same. There is no difference in the weights before and after. There is no difference in the ages between a man and his spouse. These are the hypothesized values. So I am taking that mu d, which is the differences, hypothesized the difference between those two dependent samples of data is 0. But what I'll do is, once I have collected the two samples, I'll find out what is their mean difference. Let's say the three data I have collected. Okay, man is 23, his spouse is 20. Another man is 32, his spouse is 28. Another man is 41 in my sample and his spouse is 29. So the differences, here the difference is 3, here the difference is 4, here the difference is 12. So I may find out the mean difference in all this 12 to 19. So the mean difference may work out to some 6.3 something. That is what will be my mean difference from the sample But mean difference from the hypothesization, actually I am hypothesizing that there is no difference between a man and his spouse, right? And so I am taking that to be 0. Then the standard deviation or the standard error comes out as SD by root n. SD is not of the original data, but the standard deviation is on the differences. And so the SD by root n, that is what we are applying a t statistic for. And after that, you know the story. You take the critical value based on the degrees of freedom, because here it is only one value, because we are taking the difference of two values and finally arriving at only one value, and then finding out the mean and the standard deviation of this list. We say from there it becomes just a one sample test itself. One sample test was discussed in our previous chapter, the one sample value being hypothesized to a specific constant, which is 0 in this case. So the degrees of freedom will be n minus 1, and based on the alpha you can find out the critical value, and based on the critical value you can take your call whether to reject the null hypothesis. When you are rejecting the null hypothesis, it means your mu d cannot be 0. The mean difference between the two samples of data is not 0, which means there is a significant difference that is existing in the ages of male and female, or I can say there is a significant difference in the weights of the people before and after the medication. So in those kind of cases, we will depend on dependent sample test. Even that also uses the t-test. And similarly, if I want to find out what is the confidence interval of that difference, so the same, from the sample you got d bar. So you subtract the margin of error or you add the margin of error. And as we have discussed, the margin of error is nothing but the critical value. So because we are using a t distribution, the t value corresponding to the 95% area multiplied by the standard error. Standard error is s by root n. So this is what is the margin of error. You subtract the margin of error, you add the margin of error, and if you have to make the conclusion regarding the population using this confidence interval, you check whether 0 is present in this confidence interval. If 0 is present, then we cannot reject the null hypothesis. And if 0 is not present, we are rejecting the null hypothesis and simply saying there exists a difference between the before values and after values, or there exists a significant difference between the ages of male and his spouse. So all these kind of conclusions can very well be made from the observations of the data. Then we also have a mechanism where we may have to test on the variances between the two samples. Again the same scenario. In our earlier chapter we talked about comparing the variances with a fixed constant. So there we were using a chi-square test. But if I have to compare the variances of two different sets of population, which is like saying the variance in the heights of Indians is same as the variance in the heights of the Americans. So here I am not comparing the variance with a constant, but in fact I am comparing the variances with the variance of another population. In that case, the test which I would be using is called as a F statistic, which is simply S1 squared by S2 squared. The variance of the first sample, I am taking two different samples because I have to compare the variances of two different populations. I am taking two different samples, finding out the variances, sample variances of two different samples, making S1 squared, S2 squared, then simply dividing S1 squared by S2 squared, and make sure there when you are computing this F statistic, make sure that S1 square is the larger of the two, which means this ratio should always come out to be greater than 1. Right? S1 squared by S2 squared, make sure that S1 is always greater than S2, or S1 squared is greater than S2 squared, which means the ratio should come greater than 1. And because we are using F statistic, even the critical value should come from the F distribution. Now, this F distribution is also more like your chi-square distribution only, but the difference is its critical value will depend on 2 degrees of freedoms. n1 minus 1 which is for the first sample, n2 minus 1 which is for the second sample. So based on the 2 degrees of freedom, 2 separate degrees of freedom, n1 minus 1 for the first sample, n2 minus 1 for the second sample, based on these 2 different degrees of freedom and the level of significance, the F test will give a critical value. Then again the same, as long as your test statistic is lying within the critical value, then you don't reject the null hypothesis. If your test statistic is lying either below the lower critical value and above the higher critical value, then we are rejecting the null hypothesis and saying the variances are clearly different between the two samples of data. For that to exist, a few things that we have to be comfortable with is the population should be really independent, right? This cannot work for dependent samples, and samples are simple and random. And just like the way we have used for individual variance comparison, both the populations need to be normally distributed. Otherwise, I may have to convert them into normal by doing the appropriate transformations. And a few more information about the F. F can never be negative because it is S1 squared by S2 squared. The minimum value will be 0. F can never be negative. So the exact shape of F changes with the degrees of freedom because it is dependent on 2 different degrees of freedom. The F distribution is also like a skewed distribution, just like your chi-squared, but it is purely dependent on 2 different degrees of freedom because it is always for the comparison between 2 different samples of data, their variances. So F is always based on 2 different degrees of freedom and the level of significance. So the critical value of F is also designed from that standpoint itself. And so it always depends that your data is normally distributed. Otherwise, whatever the conclusion that you are going to get, it is pretty much biased. And if the variances of the two populations are equal, then F is coming out to S1 squared by S2 squared, which will come out very close to 1, which means in that case I can directly make a conclusion that the variances of these two populations are going to be, there's not much of a difference between the variances of these two populations. Sometimes a small modification to the F test is also done. It is going as a t test. The F test gets modified. Instead of using F equal to S1 squared by S2 squared and then finding a critical value and then accepting or rejecting the hypothesis, there is a Levin, Brown and Forsythe test, which is an alternative to the typical F test. What it says is, yes, you have already taken 2 different samples. If you are going with the F test, you are taking the variance of this sample separately, variance of this sample separately, calling this as S1 squared, calling this as S2 squared, then finding out the F and then matching it with the critical value and then taking the appropriate decision. Whereas in this test, what we will do is each value, each sample value, you subtract the median. This particular, only the median corresponding to this data. You subtract the median from each individual data, which is the exact middle value from each individual data. Even here also you subtract its corresponding median from each individual data. So they'll become 2 new transformed samples, which is like the sample 1, which is the original values minus their corresponding median. Here also original values minus their corresponding median is sample 2. Again, the two populations are completely independent, right? The sample 1 minus its corresponding median, sample 2 minus its corresponding median, whatever are the two that we have got. On the top of them, create a t-test of equality of means for independent samples. Independent sample t-test which we have done earlier, wherein you find out their mean. So assume that this is x1 bar, this is x2 bar. So assume that the hypothesized difference of the means is 0. So take it as x1 bar minus x2 bar minus mu1 minus mu2, which is going to be 0. And here you take it as s1 squared by n1 plus s2 squared by n2. So the S1 squared is computed on this new sample, S2 squared is computed on this new sample. The N1 and N2 are not going to change because for each value you are subtracting the median from that value. So the number of sample items are not going to change. So this is also a kind of alternative to the F test, which will be doing a comparison of the variances only, but actually you are not computing the variances. You are actually doing a comparison of the mean, but because you have subtracted the median from each of the values, if the sample differences are going to be 0 after you subtract the median, then we can say that the variances are not going to be different. But if they are very much different from 0, then we are going to say that the variances between the two are going to be different. This is a modification to the typical F test going with Levin, Brown and Forsythe test. So this is what we have in this particular chapter. Just an extension to our previous chapter. In the previous chapter, the focus was primarily on one single sample, which means the population parameters like standard deviation or variance, mean and proportion. You have compared them, you have tested them against a constant value, whereas in this chapter the focus on the same proportions, mean and the variances, but the comparison is with another populations or some other dependent values, proportion, mean or even the variances. So the major differences that have come is for each of the things the test statistic is different, the distribution that it is going to use is going to be different, and based on that you have to find out the corresponding degrees, corresponding critical values based on the degrees of freedoms as well as the level of significance. And after that your accept and reject criteria or reject and fail to reject criteria are remaining the same. So the moment you have a solid understanding about the concept of hypothesis testing, you can very well apply the statistical significance measures to any kind of data. So we are now comfortable with almost 10 different types of claim testing. In the earlier chapter we have looked at 4 5 different claims. Here we are talking about another 4 to 5 different types of claims. Now you try to look at any kind of statistical analysis people are doing, any kind of conclusions people are making, they would fall into one of these categories. So now you have to try to link your business requirement with this particular statistical tools. The moment you are able to link that, you can create lots and lots of statistical conclusion, which means you are using data to make decisions in a very effective manner. I hope you are clear with these different concepts relating to hypothesis testing when it involves two different samples. If you have any further queries regarding this, I suggest you can get back to me by giving me a call on the number 98480 You can even email me your doubts on vamsidhar@pacegurus.com. I suggest you also visit our website www.pacegurus.com to have an understanding or to get updates regarding the various training and consulting programs, as well as the newly recorded videos in the areas of finance, investments, statistics and analytics using tools like Excel, VBA and SPSS. I hope this session gave you a good insight into the hypothesis testing involving multiple samples. Thanks a lot for listening to this session. Thank you very much.